So here we're asked to consider the simple pendulum model, which has been given to us in a differential equation. So it tells us T is a torque, the mass and the length here are constant values, and we need to linearize this model now to find the transfer function theta dash on T dash for a steady state torque of 3 Newton meters. So I'm going to follow through the process I talked about in the recap video. So the first thing there is to identify your equilibrium position. Once you've got that, you can apply Taylor series about that equilibrium position in order to find a new equation. And then the last step is then to swap over from being in T and theta into theta dash and T dash, which are the deviations from steady state. We do that because then it's really easy to rearrange it into this transfer function. Alright, so let's start off with, we'll go with step 1. This is going to be identifying our equilibrium position. So we've been given a bunch of information. We've got the mass and the length, and we've been told our steady state or our equilibrium torque here. So just scanning through this equation, we know that at equilibrium all of our time derivatives are going to be equal to 0. So here we've got theta double dot. So if we're looking at it at equilibrium, which is when I put the bar over the top, it's going to have to be equal to 0, okay? It's not accelerating. If we look through here, m, g, and l, they're just going to be random constants. We've got theta though, which can change over time. So if we draw the bar over the top, okay, that's our equilibrium theta, and that's something that we don't know, so we're going to have to figure that out. The last one we've got is t, which we know can change with time. Alright, that's our torque, and we've been given the torque that we're kind of interested in. So that's going to be the 3 Newton meters. Alright, so let's substitute into this equation, and basically then we just need to find this equilibrium theta value. So we're going to get ml squared times, well, at equilibrium, theta double dot was equal to 0, plus we've got mgl, which are just random constants, times sine of, I'm going to put this as theta with the bar, okay, our equilibrium theta, and it's equal to our equilibrium torque, which we know is equal to 3. So I'll pop that in. So now it's just a case of rearranging for theta bar. So this disappears. So sine of theta bar equals 3 on mgl, and I may as well sub those in. So m was 1, g is gravity 9.8, and L is 0.5. And if we want theta bar on its own, all we have to do is take the sine inverse of this, and we can calculate in a calculator. It comes out to 0.66 radians approximately. Okay, so this is going to be our equilibrium value for theta. So that's pretty much step 1 complete. So step 2 now is going to be to apply our Taylor series about equilibrium. I'll put TS about EQ. Alright, so how I like to do this for our control problems is just to put everything onto one side of the equation and linearize the whole thing at once. Even though in this case the only thing that really needs linearizing is this middle term here, which has the sine and theta tied up. Okay, this is already linear because that's just a constant out the front of theta double dot, and this is just t on its own. Okay, but nonetheless, I'm just going to do the whole thing at once, and then we just get the whole equation at once, and I think it's a little bit easier. So let's say that I shift across this t to the other side of the equation. So that means that when everything's on the one side, we end up with this. Cool. And then how I'm going to do it is I'm going to say, okay, I'm going to make this a function of everything that changes with time. So if we look through, we've got theta double dot and theta changing with time, and also t. Okay, so let's write them all out. Alright, and it's just going to be set equal to what we've got here when I shifted everything onto one side. Alright, so the next thing that I'm going to do is take my derivatives, and we're going to evaluate them at our equilibrium position because we know that that information gets fed into our Taylor series expansion. So let's start with the first one, which is theta. So if I take the derivative of f with respect to theta, looking through here, this doesn't have a theta, so its derivative would go to 0. This is where the theta sits though, so we are going to have a derivative here. It's going to be mgl, sine is going to go to cos, and we've got theta in there, and the derivative of just a random constant with respect to theta is going to go to 0. So that's what we end up with. So now we want to evaluate this at our equilibrium position, okay? And if I scroll back up, let's fill this in. So we know that our equilibrium theta now is 0.66 radians. So we just need to substitute these values in, and I think the only one that we've actually got to sub in is going to be this 0.66. Okay, I'll pop in the others at the same time. These are just constants. So mass was 1 times 9.8 times the 0.5, and this here is our cos of 0.66. So if you put that into a calculator, it ends up being approximately 3.87. Okay, so that's the first one evaluated. So let's move on to the next one. We need to take the derivative of theta double dot with respect to f. Alright, so looking here, we have got a theta double dot here, so the derivative of that with respect to theta double dot is just going to end up being the constant out the front, and it doesn't appear in either of these terms, so the derivative goes to 0. So if we then want to evaluate it at our equilibrium position, okay, remember that's where we substitute in all of these equilibrium values, what we're going to find is that actually we don't have any of them, it's just going to be dependent on these two constants. So 1 times 0.25 squared, which is 0.25. Alright, so we just have the one left, which is evaluating our derivative with respect to t. Oop, not up to the equilibrium part yet. So if we scroll back up, haven't got a t here or a t here, so those derivatives go to 0. But we have a t here, so when we take the derivative, it's going to go to -1. And if we evaluate this at equilibrium, it's just going to still be -1. Okay, so these are our values which are going to end up being substituted into our, just highlight it there, into our Taylor series. Alright, so let's write out our Taylor series expansion. So we have a function of our three variables, it's theta, theta double dot, and t. And I should write this as approximately, because we're only doing an approximate thing here. And we evaluate it at the equilibrium. So there are points of interest with the bars over the top. Plus, and then it's each of our derivative terms evaluated at equilibrium, times by the difference between the value and its, I should have said variable and its equilibrium. Okay, so we're going to have three of these terms since we have three things here in our function. So let me just pop that in. Plus, last one, t minus t bar. Alright, so substituting in. When we evaluate our function at our equilibrium position, what we should find is that this actually goes to 0. You can check it if you want to, alright, but when you substitute into here all of your equilibrium values, what we should find, is that this is going to go to 0 because theta double dot bar is 0, and then these should balance against each other, okay, because that is by definition how we ended up finding the equilibrium in the first place. Okay, so you can always check it, but every time this should end up going to 0 for these control problems. Alright, so next we need to substitute in our derivative of f with respect to theta, evaluated at equilibrium, which we found is about 3.57. Sorry, 3.87. Alright, and then we multiply by this, so it's theta minus theta bar, and I'm just going to leave it as theta bar for now, alright, not substitute in. Next, we need our derivative of f with respect to theta double dot at equilibrium, which we found to be 0.25. And again, I'm just going to leave this as is for now. Okay, and then finally, we've got the derivative of f with respect to t evaluated at equilibrium, which we found to be -1. So just go back, -1, and then again, leaving this just as is, t minus t bar. And then on the left-hand side here, our function of theta, theta double dot, and t, well, way back up here, we said that this was equal to this, and this is equal to this, which is equal to 0. Okay, so we can sub in 0 down here. Alright, so this is our kind of equation in terms of theta, theta double dot, and t. Now what we want to do is swap this over now as part of step 3 and put it in terms of the deviation variables. So that's where you get the little dash. Alright, so the general form is like if you're looking at x, then x dash would equal x minus x bar. So that's what we're going to do, except for our variables. So we've got 0 equals, we've got 3.87, which stays out the front, and this is why I've just left these without substituting in. So applying this equation for the theta variable, we can rewrite this as theta dash now. And then 0.25, now we can try and change it over to a dash, and this one here is going to be theta double dot dash. And then this one, again, same thing, transferring it over, it's going to become t dash. And this is linear. Okay, we've got constants in front of each of our variables, and none of the variables, I guess, are tied up in signs or squared or anything like that. So this is exactly what we were looking for. So the last little bit here is then just to rearrange and answer the question that we were asked once I get there. So that was to find the transfer function. So we need to rewrite this as theta dash on t dash in the S domain. So what I might do as a first step here is take the Laplace transform. So this is going to become 3.87. This is just stays as theta dash. This one, it's going to get an s squared from the second derivative and theta dash. And this one is just going to stay as is as well when we take the Laplace transform. So now I need to rearrange it. I might take the t to the other side, and I'll factorize out the theta. So we're going to get 3.87 plus 0.25 s squared. And then we were asked for theta on t. So if I divide down the t and divide the stuff to the other side, we get that. And if I want to make this look a little bit nicer, I could multiply by 4 and 4. That's going to get me a 1 in front of my highest power of s. So my final answer would be 4 divided by, I can write this as s squared plus, this becomes 15.5 approximately. And I'll put the little functions of s's in as well. Alright, so that is my final answer to this question. So that's all there is for this video. See you in another one.